Okay, what does equilibrium mean? Okay, level, balance. Okay, so level, balance, sure. Dynamic meaning, what did you say? Moving. Always moving. So, excuse me. Got a frog in my throat this time. One of the equilibriums. Gentlemen, are you done yet? You asked for an extra one, and now you're fighting over who gets an extra one. You did? You done disturbing my class, Raj?
Yeah.
No, I don't think you are.
I'm done.
Good. Where you found dynamic equilibrium last in Chem 20 is hopefully when you were talking about solutions. And when you talk about a saturated solution, you have a beaker with a pile of unable to dissolve salt at the bottom and the rest of it being a solution, right? So here let's put NaCl. So here's a great big pile of table salt at the bottom, and floating around are my Na pluses and my Cl minuses, because of course we all know that it's a soluble compound that then dissociates when it gets into the water. Everybody okay with that? But if you were to radioactively test, and they have done this, let's say the sodium ion, you would find that it sat there in the solid form, and then a little while later, it'll come in to the solution. And then a little while later, it'll go back into the solid form, and then it'll, okay. But you know that the concentration here doesn't change, right? You know that this can't become more saturated, less saturated, more saturated, less saturated. It stays the same concentration if it's saturated. This pile is the same height or the same mass the entire time. So every time one of these comes out into solution, what must be happening is one of the dissolved ones must be going in to the solid. So for every out, we have an in. For every in, we have an out. Does that make sense? So a saturated solution is a dynamic equilibrium in which you have the NaCl solid becoming Na plus and Cl minus, and at the same time the Na plus and Cl minus are coming together to make your NaCl solid. And so instead of going that arrow, we now draw this half arrow and this half arrow, because that's half the story and that's the other half the story. And we learn that we can read this equation this way, left to right, or right to left. So the solid dissociates into those two ions, and those two ions come together into that solid. Does that make sense? It's happening both at the same time. And so the equilibrium part is at the same speed.
Like both the Na and the Cl are going in and out
Right.
of the solid?
Right.
Okay.
For every one that goes into the solid, one from the solid must be coming out. And for every one that comes out, that goes in, etc. So the equilibrium part is happening at the same speed. Not just one for one, but actually the same speed. If I'm having 5 per second going from the solution into the solid, I must be having 5 per second go from the solid into the solution. Okay? So it has to do with rate. So dynamic means always changing. Always changing. And the equilibrium part is that the rate of the forward reaction, that's our new fancy way of saying reading left to right, would be forward, okay, is equal to the rate of the reverse reaction. And that's our new fancy way of saying reading right to left. Okay? The rate of the forward reaction is equal to the rate of the reverse reaction. Everybody get that? And it's constantly changing. If you were to radioactively tag something, it would constantly be moving. So another kind of dynamic equilibrium you've come up with in your past is when you learned about convection currents, like how this room is heated. This room, hopefully, is the same temperature everywhere in the room. Why? Because the hot air is rising, the cool air is falling, the hot air is rising, the cool air is falling, and so therefore the one output, the vent, or whatever they are in this room, I don't even know how this room is heated, I suppose those things, constantly circulates the air, right? The hot air doesn't stay there, so it's always moving, dynamic, but the temperature is the same throughout the room, equilibrium. Okay? All right, so we're going to take those concepts, we're going to put them into some chemicals, which feels a bit weird, but the concept's still the same. Right, so homogeneous mixture. What does homogeneous mean? The same. Homo means same. Homo sapiens, same species. Homosexual, they like somebody of the same sex. So homo means same. Okay, I don't know why that bar is there, but we'll ignore it. So homogeneous equilibrium, remember homogeneous mixture meant it all looked the same, right? So homogeneous equilibrium is where when we write our equilibrium, they're the same states. So you know in the last one, I just put, that's going to be heterogeneous. So in the last one, I just put NaCl solid goes to Na plus and Cl minus. What are these states on these ions? Aqueous. Aqueous. And then those come together and form your solid. They're different states. So therefore this is a heterogeneous equilibrium. Different states of matter. So homogeneous equilibrium would be the same states of matter.
So your dynamic equilibrium will either be homogeneous or heterogeneous?
Correct. And so I'll give you an example of a homogeneous equilibrium we've already seen. It's esterification. So for example, let's take ethanoic acid. Ethanoic acid, not propanoic acid. Plus your alcohol. Let's take ethanol. And we make carboxylic acid and then alcohol make ester and water. So in this case, there's my water because that's the easiest, and the ester is CH3C double bond O, O, CH2, CH3, where this came from this section and this section there. Remember esterification? Okay, what I didn't tell you, I just let you assume it was 100% arrow. I put them together and they all become these two things, but actually that's not true. Only because it's a weak acid, a lot of it stays together. So some of it becomes your ester and your water, and some of it stays the same. So on Friday, we're going to do an esterification lab. And in this esterification lab, you'll notice that sometimes it still smells like vinegar. Because even though you've made the ester, which is supposed to be a lovely, sweet-smelling strawberry, at the same time, you still have this vinegar smell lingering. So we neutralize the vinegar to sort of take away some of the smell, but sometimes the combination ends up smelling like stinky feet by the time you're done, if you haven't neutralized it enough. Okay, so equilibrium. Get it? Good. And then in this unit, what we're going to do is we're going to learn how companies shift that equilibrium. Because if you're making a lovely strawberry smelling lip balm and you're going to sell it for a very high marked up price to the teeny bops in the world, then you don't want it smelling like vinegar, do you? And so somehow you need to make that equilibrium go to be in your favor, where you get more of your product that you want and less of it going this way. So a lot of this unit is about how they shift the equilibrium in industry to benefit their products. If you're buying this and you're buying this and you're checking them together, you want as much of this as you can, right? You don't want to stay as your alcohol and carboxylic acid. You want to make as much of your ester as you can. So you have to figure out how your company can shift the equilibrium into being more products and less reactants. So that's what a lot of this unit is about. Yes?
So for the homogeneous, it would be the products are the same as the like the same states as the reactants?
Yes, so thank you for bringing me back on task. Carboxylic acids are liquids, right? Alcohols are liquids, the majority of them at room temperature, so ethanoic acid and ethanol, definitely liquids. And your water is a liquid, and the ester is a liquid. And so this becomes a homogeneous equilibrium because they're all liquids. Okay? Any other questions? Law of chemical equilibrium. We sort of described the equilibrium part up there. The rate of the forward equal the rate of the reaction, or the rate of the reverse. Okay? And the equilibrium law expression is what we're just about to do a lot of in a second. I'm going to describe that to you. But basically, it's represented by the symbol K, and we'll put the concentration of the products over the concentration of the reactants. Okay? That's certainly not, that we're going to get into some detail there. And Le Chatier's principle we cover as well at the end of this unit. So I guess what I'll say is these bottom three will go back at the end of this unit, or at the end of this first half of the unit, and read it and define those once you've learned a bit more about them. Okay? Okay, so the equilibrium law expression. Empirical evidence, do you know what empirical evidence means? No? In a lab. In a lab. So not theoretical, but empirical. So in other words, that esterification, why is the pH still not neutral? You formed an ester, which is neutral, water, which is neutral, your pH should be 7. But yet they dip a pH stick in it, or a pH meter, or pH paper, and they find that the pH is actually still slightly acidic. It's still like a 5 or a 6. What does that tell you? You must still have some carboxylic acid around. So empirical evidence has shown that not all reactions are 100%. Okay, they don't all form your ester and water. And so they decided they were going to try to put a mathematical relationship between the concentrations of reactions and products at equilibrium. Using the following general equation, this is the mathematical expression. Okay, so if you've got two products, A and B, and the little things represent the balancing numbers. Okay, so A and B react together, for example, carboxylic acid and ester, to give you C and D, for example, water and ester. Carboxylic acid and alcohol, I think I didn't say that. And then the little balancing numbers become little powers. So there's A to the power of A, the concentration of the chemical B to the power of B, which came from the balancing. Did you get it? Sort of? Yes.
The big number, the big letters, or the concentration?
The big numbers, the big letters are the chemical. The square brackets are the concentration.
So it's the concentration of.
Yes. Have we not used square brackets before? What about this?
We have not done that.
Chem 20? Chem 20. Did you not calculate pH?
Yes.
You used a log button on your calculator, which you had no idea what that was, so you just pushed the button. Right? There was square brackets in that thing. I'm trying to fish out if we've done square brackets in this. I think I have, but I think I've just done it on the fly and on the side. So square brackets are a new shorthand notation for putting concentration. So square brackets is concentration. So therefore this would be the concentration of H plus. 2.0 moles per liter. 0.113 moles per liter. It's a concentration, right?
Junior class change.
Okay? Right, so another thing you need to note is that pure solids and pure liquids are not normally included in the equilibrium expression. Okay? Aqueous are, gases are, but not solid and liquid. Since their concentrations do not change, there's so much of it that you don't really change its concentration. It's still 100% concentration. So whatever that is in moles per liter. Right? So it can't be dilute. If it is what it is, I can't dilute it. I can't dilute iron, a rock of iron. Can't dilute it. It is what it is. It's 100% concentration, whatever that means. Okay? So we don't normally include solids and liquids unless, for example, in our esterification, they're all liquids. Then I have to include them all. Okay? So here's an example. Ca2 plus and SO42 minus, equilibrium, calcium carbonate. So every low solubility, in fact all solubilities, but especially low solubilities, will have equilibrium arrows. Okay? Remember your solubility table? So we go products over reactants because of up here, up here, up here, up here, we had the products C and D. The products C and D over A and B. All right? So we go products over reactants. So back down to something that makes sense to us. Please. Up there. Okay. So here, this is a solid. So we're not going to include it. To aqueous, we do include those. And so we would have had the concentration of calcium sulfate product over the concentration of calcium 2 plus and the concentration of SO4 2 minus, except for we've just learned that solids aren't included, and so we take this solid and we cancel it out, and that leaves a 1 on the top of our fraction, and so therefore it's 1 over those two things. K being a constant, EQ being at equilibrium.
So the formula only works for homogeneous, then if you're removing any differences?
No, the formula is still the same.
Yeah.
The formula is still the same, but you exclude any solids or liquids.
Okay. It has to be aqueous to work in formula.
No, could be all liquids.
So
Okay.
whatever is not.
So for example, let's say they're all liquids, like this esterification down here. So here's an esterification. Alcohol, carboxylic acid, ester, water. Okay? They're all liquids. So therefore I have to include them all in my K expression. So K, equilibrium constant, EQ, because it's at equilibrium, equals, and by the way, we'll have more than just EQ, okay? So towards the end, you'll have a KA and a KW and a KB for different things. Just like we had delta HF, delta HC, delta H, okay? So for now, EQ, because this is equilibrium, the concentration of my product, the concentration of my water, over top of the concentration of the alcohol, the concentration of the carboxylic acid. All to the power of 1, right? All of these are to the power of 1 because the balancing numbers are 1, 1, 1, and 1. Okay? So the question goes a little like this. Write the equilibrium expression for, and eventually, by the way, we'll be putting numbers in here and doing calculations. Okay? Eventually. So write the equilibrium expression for question 1. What would we do? First of all, is it balanced already for us? Yes. Okay, so K EQ equals the equilibrium constant equals the concentration of my products over the reactants. So what products have I got? So square bracket COCl2 square bracket over square bracket Cl2 square bracket times square bracket carbon monoxide square bracket. We're good at products of reactants. Next one. KEQ equals, and it's lowercase k by the way, equals products of reactants. So Raj, square bracket what?
SO3.
Good?
To the power of.
Very good. Power of 2. Everybody get why he squared that? Because of that number there, that goes there. Divided by square bracket SO2 square bracket square times O2. Everybody okay? Okay, do the rest. Pay attention. If they're heterogeneous, you're not going to include solids and liquids. Thank you.
So that rule only applies for if they're all pure liquids, but not if they're all pure solids.
No, I would include if they're all pure solids.
If they're
as
all
well.
pure solids, then you include them all.
Yeah.
Okay.
No, I'm just like
For like 1 year.
That's what I do every question.
Because I was actually
Are you done all of them? Because it sounds to me from that noise level that you are done. Okay. Right, check your answers to 3, 4, and 5. Why is 5 what? Products over reactants. Thank you. Thank you. Sorry? Where? I need to make that smaller. Not that small. AG plus. Yeah. Sorry. Okay, check your answers now.
Is it a carbon cell?
Yeah, that's her best. I can't tell that.
Okay, done?
So then, they're just over one.
No, yeah, they're over 1. What, can we at the front stop talking, please? Thank you.
Is the state of 7?
Right, I'm moving on to number 6. And so, oops, KEQ would equal CH3COO minus times H plus over CH3COOH.
How's that one different?
Pardon?
How does that one differ from the others? Like,
From which one?
well, 4 and 5.
Because 4 and 5 had a solid at the start, and this has an aqueous at the start. And we don't include solids, but we do include aqueuses. Okay. 7 would be your carbon monoxide gas squared over your oxygen, but not your carbon, because carbon is solid. The muttering is driving me nuts up here. And number 8, they're all gases, so you're going to include them all. So KEQ is HI squared over H2 times I2. I think you need to remember that I do not expect you to be perfect when you're learning. And I do not expect you to be saying, ha, I told you.
No, we're
To
talking
those-
about the symbols. Like, we can tell those are extra G.
that?
Boys, I've got a pretty good pulse on the feeling in the room. Got it?
Where'd
Just tone it down a little bit. Not a competition.
Yeah.
Okay. Gentlemen, thank you. Okay, so these k numbers, the constants, they have actual numbers to them. Okay? If the k value is high, it means the products are favored. Because if the k value is high, it must mean that the top was a big number. Right? For this to be big, this must be big over something small. Like 1,000 over 1. Or 1,000 over 2 would make a big number still. So if k is big, it means that the top is big. The top are our products. So that means I have a large concentration of products and a small concentration of reactants. So in other words, I've drawn this arrow to say a lot of this stuff is formed and just a little bit goes back that way. So this and this come together a lot to make carbon monoxide. But just a tiny bit stays as carbon and oxygen. Or is decomposed into carbon and oxygen, I should say. Does that make sense? And again, we're talking about rates. So this is fast, this is slow. Nope, they're equal rates still. That's fast, that's decomposing the same rate, but not as much of it is decomposing. Yes, that's right. Okay, oh, and it's temperature specific, which is why I tucked in a little temperature there. Next one, if k is low, the reactants are favored. So for the exact same reason, if this is a small number, then this must be small over something large. And so you have something small over something large, and so now this is very small number indeed. And actually, that means that if it's very small, it means that these are favored, right? And what do you know about silver chloride and silver bromide and silver iodide? That they're, last year you should have sort of come about that they are precipitates a lot. They're low solubility. And so therefore it makes sense that very little of it decomposes and most of it stays as a solid. So that makes sense from your Chem 20. This is what it means mathematically, that the K constant, the equilibrium constant, must be very small because your products are not favored, the reactants are favored. Yes, Liam?
What units do you use for the K value?
The K value units change for each situation. We'll get there when we start plugging in numbers. Okay? And here, sometimes the favor, whether it favors products or reactants, is expressed as a percentage. So for example, 1% ionizes, Craig, and 99% of it stays together, making this a weak acid because only some protons are available. Yes?
So does that mean it favors the reactants?
That's right. That means most of this stays together as this. And so if we were writing an equilibrium expression for this, which I think you already have done, up there. It would mean that this would be a very large number, that these would be very small numbers, and so therefore your overall KEQ would be small. Okay? Okay, and then I think we'll maybe stop there, except for with the last 15 minutes of class, I want you to flip to that page there. And they're actually going to get you to plug in some numbers for your calculations. You won't be able to do percent reaction. Well, yes, you can. Go back there and see if you can figure it out, because it's not hard. And then, yeah, so that's what you're going to do right now. You're going to do page 61, just the circled ones, please. Just 2 and 4. Yes. Yes, yeah, go. Any questions?